Hello, everyone, and welcome to this episode of Science with QuEra. Today, we have two presenters, Jonathan Wurtz from QuEra and Kohei Nakaji from NVIDIA, and they're going to present their co-authors on work called Quantum Circuits. It's a game, a reinforcement learning a reinforcement learning agent for quantum compilation. My name is Yuval Boger. I'm Chief Commercial Officer of QuEra. I'll be hosting this webinar. I'll start with 2 or 3 minutes of introduction to QuEra and set the context for this work, and then hand it over to our speakers today. At any time, you're welcome to put questions in the chat, and we'll be glad to answer them after the presentation. So QuEra is located in Boston. We develop quantum computers based on neutral atom technology. Lots of people believe that neutral atoms are the most promising approach to creating fault-tolerant quantum computers. Our work is based on science developed at Harvard and MIT, and of course, since then at QuEra as well. And we'd like to position ourselves as your quantum innovation partner. Quantum computing is a journey. And although some people think otherwise, the true usefulness of quantum computers will come in a few years. And so we see both governments, high-performance computing centers, and enterprise, they want to find a trusted partner with leading-edge technology and wonderful scientists to help them make the most out of quantum computing, and we think we are that partner. We've got a lot of experience doing this. Our computers are available on AWS since November of 22, and we've also installed on select customer locations. You'll see in a moment a picture of a computer that we installed in Japan. We're well capitalized to be on that journey. We recently raised $230 million, led by Google and SoftBank, with participation of many of our existing investors. And we're hiring, we're growing the team. And so there are plenty of exciting open jobs at the careers page on QuEra. And as I mentioned, we partner with enterprises, HPC centers, and governments in their quantum journey. Why are neutral atoms interesting? For many reasons. Let me just name a few. The first thing, actually starting from the last bullet, is that they're natural. They're perfect. They're perfect in the sense that we could take 1 billion qubits. In our case, each qubit is an individual atom, and they'll be perfectly identical. There are no manufacturing defects. There are no inconsistencies. And that makes our lives and our customer lives much easier. Neutral atoms can exhibit high fidelity and long lifetime. They operate at room temperature, which makes these computers very easy to install at HPC centers, very modest power requirements, and no need for cryogenic cooling. Our atoms are placed approximately 4 or 5 microns, that's 4 or 5 millionths of a meter from each other. So you can imagine that we could put many qubits on a single computer. We think we can reach tens of thousands of qubits on a single machine, and that's a contrast from other approaches that require optical interconnects, which make compilation more difficult, which lowers fidelity, which makes systems more expensive. So we think we've got a really nice path to scalability. But the reason we're here today is that one of the interesting advantages of neutral atoms is all-to-all connectivity. We can shuttle, we can move around neutral atoms. When they're far apart, they're indifferent to each other. When they're close together, we can make them interact. So essentially, we can reconfigure the connectivity. So as you compare it with modalities that have fixed qubits might have, each qubit might be able to interact with 2, 3, 4, maybe 6 adjacent qubits, where we have all-to-all connectivity. And so to take advantage of that, this is essentially one topic in this webinar. By the way, the picture on your right is a picture of a system that we recently installed at AIST, the National Institute of Advanced Industrial Science and Technology in Japan. This is a gate-based machine, and we're very excited about this installation as well as others that are coming. I want to show you a brief video from a paper that was published by a research that was led by Harvard with participation of MIT, QuEra, National Institute of Standards, and University of Maryland. And it showed at the end of 2023 operations with logical qubits. And what you can see here in this video, which has been dramatically slowed down for human purposes, is you can see this qubit shuttling. You can see that we can move groups of qubits, and when they're close together, we can make them interact. When they're farther apart, they're indifferent. So a big part of the algorithm is decide which qubit to move when and where. And I think that's perhaps a good segue into the presentation. And Jonathan, would you like to start?
Yes. Let me. Good. All right. So as you've all very nicely lined up, one of the key features of our devices is mid-circuit reconfigurability. This was first shown in a paper in 2022 by our friends over at Harvard, where you're basically able to move qubits around in your array in order to do gates between local qubits. And we've since taken this idea and run with it, and we have this notion of these reconfigurable atom arrays with zoned architectures. So this is sort of a simple animation of what this might look like, right? Where we have multiple regions. Say we have some storage region, which can have many qubits or individual atoms in sites, and we have some entangling region where pairs of qubits can be entangled with each other using a single zoned gate beam, which is able to implement controlled Z or other phase gates between neighboring pairs of qubits. Then the challenge, right, is now you need to basically move your qubits using these dynamic AODs, or AOD is an acousto-optic deflector. It basically makes a grid of trap sites that move you between different sites, and you're able to do this in the middle of your computation, and therefore you're able to have this efficient reconfigurable connectivity. And this is the key feature of this device. And of course, the challenge is how do you actually figure out which atoms go where under these AOD constraints. And in fact, as you've all said, this machine, which we're calling Gemini, is our upcoming machine, which, as you've all described, it is being built up in ICE at Japan, and hopefully, at some point soon will be available for use. It is, a quite capable machine. Order 200 qubits, high fidelity gates. Sort of, one might imagine it's a similar capability in terms of number of qubits as our current generation device, QuEra, except now this is this reconfigurable gate-based mode, as opposed to, our previous generation analog mode. And in fact, a previous demonstration on a Gemini class device in Boston, we did an experimental demonstration of something called logical magic state distillation, which is to say you basically have magic states, which are sort of resource states for fault-tolerant computation. And we demonstrated being able to break even in terms of improving the fidelity of these magic states using while encoding them into small color codes. And then this is the actual animation, like these are actual pictures of atoms as they're moving around in order to actually execute these circuits which implement this distillation. So the challenge, of course, is that when we're doing this reconfiguration, we need to do so under constraints of the AOD, right? And in particular, right, what we might want to do is to reconfigure, right, which is to say, I want to go from atoms in this set of locations to this set of locations. I want to say, I want to move atoms from locations here, like these initial locations to these new locations, right? But the challenge is you're not necessarily able to do so all in a single step. And this is because the AOD has certain constraints to it. In particular, when you pick up, you basically always have to have the AOD on a grid. So this gives us two major constraints on a single AOD move. The first is a many to one constraint, which is to say, if you have two rows, right, say, row 1 and row 2, those two rows cannot go into a single row, right? And so in this case, row 1 and 2 cannot be squished into a single row. And the second constraint is then the crossing, crossing constraint, which is to say, I guess in this case, this is columns, right? You're not able to take a column or a row and flip the order. So in order to flip the order, you'd have to move them, put them down, and then take a second move and move those, right? So in this way, actually, in order to do an arbitrary sort, which it turns out you can do in a logarithmic depth, you need to basically do this by doing multiple AOD, picks, moves, and drops in order to actually do your resorting. So these are our conflicts, and then this is what motivates an objective function. So in particular, what we can do is define something called the conflict graph. So the conflict graph is a graph of vertices and edges, where each vertex is an atom that needs to be moved, and each edge indicates that the two moves cannot be done in parallel, right? So for example, if I have a move where I start out, with two atoms in, different rows and I move them to the same row, then I would not be able to do those in the same move. What this means is that a valid parallel move is an independent set on this conflict graph. And by extension, a valid reconfiguration, which is to say, moving all of these atoms to a new set of locations, ends up being an edge coloring, where each color denotes an AOD move. So for example, if we wanted to move these atoms, A, B, C, D, E, F, to these locations, this is the conflict graph that arises from that. And then if we color the vertices of this graph, this gets us the different parallel moves that we need to do in order to execute this. So in this case, we have 3 different parallel moves in order to implement this reconfiguration. And of course, as everyone knows, vertex coloring is an NP-complete problem. But I guess heuristics, as always, are our friend. And there's a few useful theorems which show that we can get very close to optimal with efficient classical algorithms. So what we can do then is, using this conflict graph, we can define a reconfiguration cost, which then acts as a combinatorial objective based off of the number of atoms moved, the total number of moves, as well as the distance traveled. So for example, if I have an atom which moves from here to here, that's a longer range move, and therefore will have a slightly higher cost than an atom that moves from here to here. And a key point here is, we can imagine sort of a statement or a command to our processor, which is just reconfigure from this state to that state, right? And actually, when we're doing this statement, we don't actually explicitly program the exact AOD moves. Instead, what we can do is simply look at the structure of this conflict graph and use the structure of the conflict graph to then estimate the number of moves. In this sense, we can just estimate it based off of the connectivity of the graph, or the number of vertices of the number of edges of the graph, in order to estimate the total reconfiguration cost. And in this way, we're able to say, given some reconfiguration, this is the cost of that reconfiguration. Great. So, of course, all of this is in the context of move synthesis, right? Which is sort of similar to the problem in superconducting, the swap networks in superconducting qubits, where at one level you have an abstract circuit, which is completely disconnected from any physical hardware, and you actually need to map this onto actual physical qubits, or maybe groups of qubits for logical moves, and then need to figure out how to actually move those qubits around mid-circuit. And this is this growing subfield of move synthesis, right? Where now you go from, some big circuit with lots of, arbitrary connectivity gates, and then you can go and say, okay, now I need to take this graph, I need to move these guys down here, and then these guys down here, and so on and so forth. And in this way, I'm actually able to, in a forward sense, execute some circuit. So in this case, I think this is a very naive move synthesizer doing I think a graph state preparation. Good. So of course, the the thing we can ask is, what are different strategies that we can use for the smooth synthesis question? And there are many different strategies, but the one we chose to explore and pursue in this paper here was, what if we used AI, or specifically reinforcement learning, to actually design what this reconfiguration is. And I think maybe this is a good place to pass it off to Kohei. So maybe you can take it over.
And
Thank you, Jonathan.
And Jonathan, sorry, Kohei, while you're loading the slides, I do want to ask Jonathan one or two questions. Maybe I should have covered them up front, but why do we need moves at all? And how is this related to both zoned architecture as well as perhaps parallel gates?
Yeah, that's a great question. So we need to do moves because, oops. Oh, I guess Kohei is showing the screen now. We need to do moves because actually, in order to do a gate between qubits, they need to be adjacent to each other. So we need to actually take our qubits and move them from far away in the memory region to close together in the computation or the entanglement region. And sort of this would be why we'd have to do these moves.
And also, I think that in our computer, there are multiple zones. Maybe there's a storage zone, an entanglement zone. I think if I remember correctly, in the storage zone, qubits have a long coherence time. They live for a long time. In the entanglement zone, we can make the operation. So we need to move them back and forth. It's almost like a CPU moving data from memory into registers, performing something on them, and then placing that data back. Is that correct?
That's correct. And actually, one of the very cool things about these reconfigurable architectures is similar to our capabilities on Aquila, where you're able to place atoms arbitrarily in 2 dimensions. You also have a lot of flexibility, possibly in terms of how to specify your zones, right? Because, for example, if you want to have 2 zones or 3 zones, or if you want to have, your L1 cache, your L2 cache, your disk memory, your measurement region, your entanglement region, a second entanglement region, some, replenishment region, so on and so forth. There are many different options in terms of actually even designing what these zones look like. And that's actually one of the very exciting things about, I guess, reconfigurable atoms is our flexibility.
And so because generally there's no free lunch, taking advantage of these requires some clever algorithms to decide what to move and when. And Kohei, maybe you can explain the approach that you took in this paper.
Yes.
Yeah, thank you so much. I'm Kohei Nakaji from NVIDIA Quantum team. Before starting my part, let me briefly introduce about NVIDIA in quantum computing in one slide. So NVIDIA doesn't build our own QPU quantum computing, but instead we support quantum computing through high performance computing. So we provide a solution like supercomputing architecture connecting quantum hardware. We provide ability to run hybrid algorithms using GPUs, QPUs, a software platform that seamlessly connects hybrid applications, and also the ability to perform qubit agnostic development of control and error correction. And we also have recently also focused on the AI use of quantum computing. So the atom game, which I present today, is also one potential direction where NVIDIA can help quantum computing. In a very high level, atom game is a game to move atoms for quantum circuit execution. The AI agent called quantum circuit daemon is trained to generate reasonable atom moves by playing atom game many times. Then at the inference, the AI agent quantum circuit daemon generates the move for the target circuit. So in more details, the task we target is as follows. So as a preparation for the game, we first decompose the quantum circuit into parallel executable components in the circuit level. So the decomposition can be anything, but we greedily break it down into components that can be executed in parallel. And we also ignore 1-qubit gate, which is executable without moving atoms. So basically, what we focus on in atom game is generating atom moves for 2-qubit gate execution. But it is not just the reconfiguration only for 2-qubit gate execution. We also have an process called a reconfiguration of the layout. So this reconfiguration of layout is like just changing the layout for the future gate execution. Then atom moves for 2-qubit gates execution are generated for a given layout. And this 2-qubit gate execution for a given layout is well studied in previous literature, and also it heavily depends on the strategy to build the architecture. So we define our framework of atom game as agnostic with the gate execution part. So in atom game, we generate atom moves for the reconfiguration of the layout of the atoms, assuming that there exists a protocol to perform the gate execution for a given layout. In more details, the atom game is defined as follows. The AI agent changes the layout before executing the circuit component. And then the atom moves required to execute the component are generated. I want to emphasize that this reconfiguration is performed not only for the current circuit component, but also for future circuit components. And the objective of atom game is minimizing the cost, logarithmic infidelity defined by the summation of the cost for reconfiguration of the layout and the gate executions at each step. So we don't even need to construct the actual process for reconfiguration and gate execution. So as long as we can estimate the cost for reconfiguration and gate execution, we can train the AI agent to minimize the cost. And in this work, instead of defining the actual reconfiguration and 2-qubit gate execution process, we estimate the cost function. The cost estimation used in our experiment includes the infidelity due to the atom loss and the decoherence, and the constraint for the AOD laser, which Jonathan already explained, is also important because it determines if like two moves are parallel executable or not. So those things are considered when we design the cost function estimation. I want to mention that there is a trade-off for the layout change. The more layout changes may lead to the efficient gate execution, which reduces the value of the cost for gate execution G. But the layout change takes time and leads to the atom loss as well. So that's why it leads to the increase of cost for reconfiguration L. So that's why learning how to efficiently perform the layout change in parallel is a key success factor of the atom game. The layout change is autoregressively generated. Atoms we move are the ones included in the subsequent circuit components, and the model determines the move for each atom one by one. The move generated is used in the next step to generate the next move. And if the current position of the atom is generated, it means that the atom is kept in the same position. Also, the position already filled with the other atom is prohibited. So as I mentioned, the model generates move for each atom one by one. Model move for the reconfiguration for each atom one by one. And the move is specified as the next position of the atom. So we can say that the model is a generative model of the next position of the atom. Let me briefly talk about the details of the model. So we use the transformer-based neural network. The last layer of the model looks like this. So these numbers, for each position, we see numbers. So these numbers are often called logits. And the probability each action or each position is sampled is proportional to the exponential of the logit. So how to construct the logits in the last layer is important when designing the machine learning model. And our model uses multiple transformer layers. The transformer is a machine learning model component using the attention mechanism. The transformer is used in large language model like ChatGPT, but it is also used to learn correlation between inputs. For example, in like AlphaQubit, which is the AI-based surface code decoder proposed by DeepMind, they use a transformer layer to capture a correlation between syndrome measurements. So in our model, we prepare two types of transformers. The first one is a gate transformer to learn the correlation between gates. And the second one is moves transformer to learn the correlation between moves. The input for the gate transformer are the subsequent circuit components, including the current atom and the layout of the atoms. Gates transformer uses attention mechanisms to assess the impact of moving atom to other, how like moving atom to a specific position affect other gates. So this component basically capture the correlation between the gate, including the current atom and the other gates. The inputs for the move transformer are already planned reconfiguration moves and the layout of the atoms. Moves transformer uses attention mechanism to capture the correlation between an additional atom move and already planned moves. So by using those transformers, we capture the correlations, and then those information are aggregated by the readout layer to construct the logits, and the action is sampled from the logits. So in summary, our agent plays the atom game based on the model using transformer and receives reward or cost. And using the reward, it updates parameters in the neural network so that a better move is generated. And we train the AI agent by using this protocol, and we use the same AI agent at the inference for a given target circuit. We run two types of experiments to validate our model and our protocol. The first one is training and testing the model on the same quantum circuit. Since the training itself takes time, so the actual use case of the first experiment is limited, but it will be useful to see how it behaves. The second one is training the model with multiple circuits and testing it with a new circuit. The details of the first experiment is as follows. So let me briefly explain about our experimental settings. So as a dataset, we create circuits from MQT bench, and we also prepared the throttlized about model Hamiltonian simulation circuit. And the first initial atom layout is randomly initialized, and we train the model for each quantum circuit from scratch. The training method is proximal policy optimization (PPO), which is often used in the reinforcement learning project nowadays. And we calculate the cost log infidelity cost reduction compared to the case without reconfiguration at each iteration. So in this figure, each subfigure corresponds to each benchmark circuit. And a horizontal axis is a number of iterations corresponding to number of praise. And the vertical axis is the cost reduction. And each curve corresponds to each random seed for initialization. So we see at the beginning of the training, the cost reduction is minus. meaning it's worse than the no reconfigurations of case. So the no reconfiguration, in the no reconfiguration case, the cost reduction is 0%. So if it is minus, which means like it is worse than the no reconfigurations. So at the beginning of the training, the cost reduction is minus, so meaning it's worse than the no reconfiguration case. But after some iterations, the agent starts to learn effective reconfiguration moves, and the cost reduction becomes positive up to like 20%. So we also plot the total number of atom moves, namely the number of actions where a different position from the current one is generated. So we see like at the beginning of the training, the like total number of atom moves is large, but then after some iteration, it becomes decreases over time, and it becomes like 20 or like so it becomes like much smaller after some iterations. This means like at the beginning of the training, the agent generates like useless reconfiguration atom moves. But after some iterations, it learns an effective atom moves for the reconfiguration and for 2-qubit executions. So that's why we observe the cost reduction after some iterations. So this is a result of the experiment 1. The second experiment is training with many circuits and testing it on new unseen quantum circuits. So at the training, we generated 30 Hamiltonians, each consisting of 40 terms of local random parity operators acting on 40 to 50 qubits. And we converted it into quantum circuits by applying 4 steps of totalization, and they are used for training, pre-training. And we pre-train the model with these circuits. Yeah. Then at the testing time, we generated new 3 quantum circuits not included in the training dataset in the same way as the above. And we compare the case with pre-training and without pre-training. And as a model, we use only the transformer part. And the cost reduction is shown here. We show the cost reduction for each number of shots. This n shot means the model plays atom games n times with the target circuit, and we choose the best result. We see that without pre-training, the cost reduction is minus, as expected. But with pre-training, it could generate reasonable atom moves even for unseen circuits. So I also want to mention that we can further fine-tune the model, though even though we did not run the experiment due to the limitation of the computational time, but we can like fine-tune the model further. And also, like I want to mention, like this is tested with just Hamiltonian simulation circuits, but in the future work, we want to try training with variety of circuits and apply it to new unseen circuits. But what I want to emphasize here is like the model shows some like transferability in this experiment. Finally, I still want to mention that we need some further discussion to apply this protocol for the practical use case. One thing I want to mention is like initialization. So initialization can be more like important than the move synthesis in some problems. For example, like for structured circuits, initializing the atom allocation can be more important than the reconfiguration. But for arbitrary circuit, the effect of the move synthesis will become more important as the circuit becomes deep. And we can also build the initialization with AI. So this, can be a very good direction for the future research, I believe. So another discussion is like, do we really need machine learning for atom game? This is an open question. And I think we can also build the like heuristic without machine learning. But at least I believe that some customizability with experimental data can always be a benefit of machine learning based one. But even for this, we need to consider a simulation to real transfer, which is well considered in the domain of robotics. So this is, I believe, also a good direction. Future research. And also, like, I want to mention about the logical computations. So our method can take care of the group of physical qubits. So it can be applied to a group of physical qubits or like logical qubit. But if we consider the logical computation, we also need much more planning for logical computations, like how we like prepare the resources, like magic states, how we apply, So this, I think this could be another Atom game, like Atom Game 2 or Atom Game 3, or like, So yeah. But it is like, I strongly believe it is a very interesting area, and I'm very happy to, discuss further with you guys. So this is a summary of today's talks. So we introduced the Atom game as a compilation game for reconfigurable neutral atom arrays, and we construct a transformer-based model for reconfiguration and train it using a reinforcement learning algorithm. And our numerical experiments show that our AI model learns to generate effective reconfigurations, and we also observe the transferability of the model. Thank you.
Thank you very much. I want to mention that this collaboration between NVIDIA and QuEra is one of several collaborations that we're doing. There was an NVIDIA technical blog from a few months ago showing how AI can help with the decoding of errors. And this fits into the broader topic of AI for quantum, and then separately quantum for AI. We're also collaborating with NVIDIA as what's called, I think, a founding collaborator at the NVIDIA-QC. NVIDIA-QC is the NVIDIA Accelerated Quantum Center that's coming up in Boston, where we will work together on integrating HPC and next generation quantum computers to deliver wonderful results for the industry and for users. So this is just one of many collaborations. So with that, we'll end today's webinar. Please join us for future Science with QuEra webinars. Thank you very much and have a great day.